Hi, my name's Steve Roper and I'm going to talk to you today about our new best of breed simulator, Opt2Sim. So here at Unison we've taken our simulator to the next level. We've actually introduced a simulator that's based upon the CAD model of our real machine, so you can see the level of detail that we have modelled of the machine. Every single moving component from our machines is represented in our simulator. The simulator now does collision detection, and it also has a built-in artificial intelligence engine that can solve parts for you. So rather than going down to production to work out if a part can be bent, it can now be done in the simulated environment with full confidence that it's going to bend accurately in the real world. So I've just loaded a part in there. I'm not going to explain the engine, explain the user interface too much. I'll just explain bits as I go through. We tried to make it intuitive. It needs very little explanation. So we can see here I've just kicked off the simulator in the physics mode. So this does collision detection. The normal play mode here, PL, ignores any collisions and just plays through the part. The physics mode does collision detection, and the AI mode, the artificial intelligence mode, tries all of the different combinations. It knows what the machine is capable of doing, so it uses its own intelligence to work out the best, the most efficient way to bend a part on the machine. So the physics mode here has detected a collision. So if we just say OK, there we can see it shows us where the collision is. We can zoom right into that. We can take a good look around. That's definitely a collision as far as I can see. And so now if I just step back a couple of moves and then, well, in fact, sorry, I've just hit that in the AI mode. I could have worked through that. I could have pressed the buttons on the side here, the R, to switch which head it was going to work on. I could have changed other values. I can switch the rotation. I can choose to make the part from the other end. The AI mode now is running through, and it's actually going to work out the best way to bend this for us. You can see the simulator's going a bit faster now. The speed of the actual graphical simulation will always be dependent upon the speed of the graphics card in your machine. When we process things in a batch mode, which I'll demonstrate in a short while, you will see that we choose not to show the graphical representation because working just the collisions out mathematically is so much faster. So whilst the speed of the simulation is dependent upon the graphics card in the machine, the cycle time here in the top right hand side will always be accurate because this is worked out mathematically using everything that Unibend knows about the machine and what the simulator knows about the modifications it's made to the YBC file to give you a correct value, a correct cycle time. The speed mode here next to the cycle time shows you, allows you to change the speed of the actual simulator. So if you want to see it going slower, then you have the option to do so. The line here lets you start the simulation from any line. We can also do that just by stepping through the lines here and just choosing whatever mode we want to go into. So in this instance, the simulator was able to successfully bend that part by modifying the YBC file. If I wanted to choose that as my solution, then I can obviously choose to export that by ticking on the arrow here, or by choosing the export function from here. Whilst I'm in this sliding menu, I'll just talk about the different camera angles. We've chosen a number of angles that you can flick through if you want to, and you can also capture a screenshot at any point in time. We can change the colour of the room, and we can also set some environmental settings. The version that we're working on next will allow you to map additional objects into the room, so if there are other environmental factors like cupboards or tables or a light curtain for a machine, then those will also be able to be modelled on the simulator. So let me just quit the simulator now. I could choose to import a folder from here, or I can just drag a folder onto the icon. First of all, let me just open up this folder, and I'll just show you that this folder here just has 4 parts in it. That's about it really. I'll just drag that onto the icon here, and now it's going to open up that simulator in a hidden mode. So if I just open up this folder now, you'll see what it's done. It's created some subfolders. We've got our 4 parts to be studied. We've got a quarantine folder, a report studied and successful. Any parts that can be made, that the simulator can find a solution using its AI, will go into the successful folder. The original unmodified YBC files will be put into the studied folder should you want to refer to them in the future. The reports folder will contain screenshots of any collision points so that we can easily send those to a designer to take a look at, and the quarantine folder contains anything that cannot be bent. Whilst that's just running through, let me just talk through a couple more bits of the simulator. First of all, in terms of, I'll just put this here so we can see the progress. It's still studying that first file at the moment. When we were making the simulator, we looked at a few physics engines, and we were surprised that none of them really were anywhere near accurate enough for our requirements. For example, the NVIDIA engine, I think, has a tolerance of 5mm. So if you're running through a game and you bump into a wall, it really doesn't matter if you go 5mm into the wall. No, it's never going to affect the gameplay. But obviously that's no good for us. In the world of tube bending, we wanted pinpoint accuracy. So we've actually written our own physics engine, which puts a skin around the entire CAD model to a depth that we can define. So by default it's accurate to 0.005mm. So it's very, very accurate. Secondly, we wanted the simulator to really truly represent how our machine moves. And of course at Unison we've got great flexibility in our control software, and we can really change the sequences of the machines on a customer by customer basis to meet any challenge that our customers may have. So we wanted to ensure that the simulator represented the true movement of a machine, and so the way the simulator works is that it calls a motion profile, and so it calls Unibend to produce this motion profile, which defines how each and every axis on the machine moves, and it uses that during the simulation process. Okay, right, we can see that that's now finished studying that folder. It looks like it took about 3 minutes, so that we've done extensive testing on the simulator, and we've found that it does simulate around about 100 files an hour, and so that's kind of in correlation with that. If we have a look now at a couple of the folders, in fact let me just go back, we'll just have a look at this studied text file. Normally if you were viewing this in Unibend, then this information is pulled out the text files and it's displayed onto the screens with a nice user interface. So here we can see that of the 4 files, 3 of them were successful, but the simulator needed to modify the original YBC file in order to come up with the solution. One of the files, and the full path to that file is located here, was put into quarantine, so the simulator could find no solution for that part, and this would need to go back to the designer. Customers looking at the simulator at the moment have noticed some fantastic cost and time savings by using the simulator to really put the responsibility for design back into the seat of design, rather than that kind of usual toing and froing of design creating a set of parts, them going down to production to be bent, coming back from production with some amendments necessary, then design taking a look at those amendments, issuing them back to production, needing to be scheduled back on the machine. All of these things introduce time delays, so the simulator now is a desktop application that the designer can run that is going to put the responsibility for the design back into the design department and reduce impact on production, speed time to production by taking all of that unnecessary toing and throwing out of the equation. So let me just take a look. And so as I say, we can choose what line we want to simulate from here, or we can just flick through. And so if I just take a look at this. Now I've just chosen this part because from memory I believe that this does some pressure die interference. So it just shows you that you know, with pinpoint accuracy, this really is doing exactly what the machine does. And so hopefully in this we should see that the clamp and the follower will come up, and then I think during the pressure die the follower is going to move away just to allow the collet to come in. There we go. Right, so I don't know much more about what I want to say. I hope that's given you a good overview of the simulator. Of course, in this incarnation we've just seen the simulator working out the best way to bend an individual part on an individual machine. So the batch process allows you to find the best way to bend any number of parts on a machine. The obvious next step for us, and what we're working on actively, is to model every machine in our range so that the simulator would not only be able to tell you the best way to bend a part on a given machine, it would be able to tell you the best machine to bend that part. So really making sure that if you've got a number of Unison machines on your site, that you would be able to schedule your work on the most efficient machines. And so really we just see the cost savings are fantastic. I think that's all I've got to say. If you have any questions at all, I'll pop my details up on the screen now, and then just please feel free to give me a call or a ring at any point in time. I'm always happy to talk about our simulator. It's only through interaction with our customers that we're able to deliver exactly what is wanted, so all feedback is very much appreciated, and any ideas would be greatly welcomed. Thank you very much. I hope I've not gone on too long. Take care. Bye bye.